So welcome everyone to VQMS. Today we're going to have Soheil Ghili from Yale talking about second degree price discrimination. The way the webinar is going to work is the panelists can interrupt anytime to ask questions, or you can raise your hand and I will direct questions to you. The audience can type in questions into the Q&A box, and I will collect all of your questions and relay them to Soheil periodically. Um, and I think that's it. We have an hour for the formal presentation, and then we'll stay back for 15 minutes of informal discussion right after. Right, Sohail, you can take it away.
All right. Well, thank you so much for having me. This is a paper with my colleague Sudhir, and then an LBS colleague Nitish, and then Ankar Garg from AirAsia. We will think here about second-degree price discrimination. We do theory, experiments, and empirics. All right. By the way, do you see my cursor as I move it? Oh,
Yes, I
okay,
do.
good. So then I could use it to point to things. Okay, so let me start with some background. Second-degree price discrimination is ubiquitous. You see many examples of it around us. Perhaps the most commonly used example is quality-based discrimination. You could think about, for example, when Apple thinks about whether or not to offer two versions of the iPhone product based on memory levels. That's one example of second-degree price discrimination. And that is actually going to be one of my running examples throughout this talk in order to sort of illustrate some of the concepts that I will get to. In addition to that, tiered pricing, especially in SaaS products, is very common. That is also an example of second-degree price discrimination on the front of quality. In addition to quality, you could think of quantity as well. Any sort of nonlinear pricing design could be thought of as second-degree price discrimination. And also, timing, for example. If I say you book something early and save 25%, be it accommodation or be it flights, all of those could be thought of as second-degree price discrimination, whereas sometimes I tell my MBA students product-based price discrimination. Okay, so that's the idea. Because it is ubiquitous, there's also a large literature on it. Starting from the theory, there's of course so many theoretical papers. I'm not necessarily going to list all of them. That would be an impossible task. A particular subset of the theoretical work on second-degree price discrimination is going to give us characterizations on when it is an optimal decision for a seller to basically do second-degree price discrimination. And when you look at those characterizations, I'm going to talk about some of those later in the talk. When you look at those characterizations, you could see that it is an empirical question. In other words, when a firm like Apple looks at the characterizations provided in many of these papers, Apple could say, okay, now I see that under condition X, I should offer two versions of my iPhone based on different levels of memory. Under conditions Y, I should only offer one version. I could see that in the paper, but could you also tell me whether I'm under conditions X or condition Y? That's the empirical question. Yes or no?
So shouldn't the monopolist always offer more versions because they can always, choose prices that would maximize their profits? Like more is better for monopolists. Is that true? Or
Okay, I would say so. If you say more is weakly better, right? But if you're offering more version, and then under those more versions, the optimal pricing is such that one of the versions is not going to get bought at all, then you're effectively offering one version, right?
okay, so that was just because you said like, oh, when should I offer one or two? Like, I guess you should always offer two, but then the prices may be very similar to the versions.
Yes, but that's the way I would think of offering one. When should I effectively offer one? Because in the real world, again, when we think about it, extending the product line, actually producing another thing is costly. We're not going to have those in our model, but I think if you talk, for example, to Apple, that would be something that they would be concerned about. They're not going to produce both and price in a way that only one sells. All right. So that is an empirical question. And then do we have empirical literature on second-degree price discrimination? Of course we do. There's a long line of literature, both in quantitative marketing and in economics. And it would be it would be an unfair statement to say that this literature is not connected to the theory literature. Actually, they are well connected. When you read the empirical papers on second-degree price discrimination, you see that the theory literature is well cited. However, I would like to argue that this connection could be further strengthened in a specific way that I'm going to describe, and that I hope to deliver on in the rest of the talk. In my view, there's no generic model of price discrimination. And by generic, I don't mean, by the way, I don't mean general. By generic, I mean a model that sort of stays agnostic on the nature of price discrimination, on the nature of the differentiation between the products. A model that sort of stays agnostic on whether it's quality, quantity, timing, anything. So that basically the model, to the extent possible, could be applied to different settings. So I would like to argue that there is no generic model of secondary price discrimination that does the following two things. First, directly builds on the screening literature so that it allows us to replicate and further build on some of these characterizations provided in the theory literature. And two, designs and implements experiments that provably identify the key parameters in those theory models under realistic constraints that firms out there would face. Let me be a little more specific about it. That basically takes us to the research objectives of our work, which is we hope to provide a theory-driven framework that firms can directly use to empirically optimize second-degree price discrimination. All right. So to this end, what we do is we start with theoretical analysis. We provide a generic model. Again, on many fronts, you may not necessarily consider this model general, but it is generic in the sense that the differentiation between the two products could be anything. It is a generic model that allows to replicate and build on some of the results on the optimal pricing mechanisms from the screening literature. It produces additional results that could guide design of experiments. And finally, this model could be cast as Berry-Levinson tickets, which will facilitate and ease the empirical estimate. So that will be the theory model. Based on this theoretical framework, we indeed go ahead and design an experiment, which, as I said, is guided by theory. I hope that I can convince you that the experiment is also parsimonious and economical. It could also help broaden the applications. And if I have time, I'm going to talk a little bit about how this approach, how this experiment design helps estimate the model with aggregate data and few product versions, which in many price discrimination cases are restrictions that firms realistically sort of expect to face. Once we do that, once we design the experiment, and we also have the theoretical framework, we basically use those to estimate our model as an empirical BLP model and basically demonstrate the applicability of the framework. We do it in two ways. Once we do it, we basically implement it in the field and show basically how the framework works. But in addition to the field experiment, if I have time, I will also show you additional simulations, which could also help further illustrate the applicability of the framework. Okay, so that's basically an introduction. In the rest of the time that I have, I will give you the model. Then I'll talk about the experiment design. Very briefly, I'll go over the estimation procedure. Then we're going to talk about an application and seat selections in flights. Finally, additional simulations, and then discussion and conclusion. Yes, Nick. I'm not hearing you.
I know that in the comparative setting, in this setup where like firms choose the quality levels and prices, there's like either there's the existence of equilibria issues. So like in many cases, equilibrium doesn't exist because like you would just only offer like high quality like undercut, and then that's not an equilibrium. And then there's like mixed strategies, and then there's multiplicity issues. So how do we think about all these things in comparative settings? Like what if equilibrium doesn't exist, or like multiple equilibria? Then what does it really mean if the firm should offer more or less? So just like how do we kind of incorporate that literature in this question?
I see. So let me start by pointing out two things. One, this is a very good question. And two, this paper does not do it. So let me start by those. We're going to look at a monopolist. What I would say is that I hope to sort of convince you that there are important things important contributions to make, even in the monopoly case, and that's worth one paper. That's the way I see it. And hopefully, the framework and the insights here could be used even by firms that are not monopolists. They could see what this framework offers, and then they could adjust based on the fact that this model is not perfect. So that's what I could say about applications so far. But if I were to speculate on how things would go if we were to incorporate incorporate competition, I would agree that both non-existence and multiplicity matter. My raw intuition says that multiplicity matters more. I'm basically thinking a little more along the lines of the Glenn Ellison paper, the economics of add-on pricing QJE. I think so. So there, basically, one insight that comes out is that in addition to what you would consider as a monopolist, sometimes it would pay to just look at your competitor and mimic their behavior. If they're price discriminating, you should too. If they're not, you shouldn't either. How to exactly give empirical weights to that versus this? At the moment, I don't have an answer. But we are hoping that that would be a follow-up. Thank you. Okay. So let me start with the model. I'm going to have two product versions. I'm going to denote them K and index them -1 and 0. The reason for -1 and 0 is that later you'll see that our application is timing. So -1 is for early purchase, 0 is for purchase at the time of consumption. But again, the model is generic. Actually, my running example before we get to the application is not timing. It is sort of a more, I would say, familiar example to everyone, which is basically an example of purchasing, say, smartphones. So you could think of version -1 as on average, lower quality phone with only 64 gigabytes of memory. These are gigabytes. These are not bytes. That would be bad for the producer of the phone. So 64 gigabytes and 256 gigabytes of memory. Think of the two products as these. This is going to be my running example, at least for the next few slides. And then you could think about the utility to individual I when they consume product version K. We could denote it UIK. There's a constant term A. There is an individual specific term UI. There's another individual specific term gamma I. This second term does not apply to every case. It only applies if you are consuming the sort of higher quality version of the product. And then, of course, you're going to have a disutility from having to pay the price for the product. Very brief on the interpretation. You could think about A plus mu I divided by B as consumer I's baseline willingness to pay, which is how much I'm willing to pay as this consumer to basically purchase version -1, the baseline version, if you will. Then gamma I divided by B, you could interpret as this consumer's differentiation willingness to pay, which is if I already have the baseline version -1, this is the amount that I'm willing to pay in dollars to upgrade to version 0. All right, a couple of additional assumptions. The first assumption is without loss of generality. We assume that mu I is mean 0. Why is it without loss? Because we have the term A. The second assumption, which is not without loss, is something about the relationship between the differentiation willingness to pay and the baseline willingness to pay. We assume a linear and deterministic relationship. Later, if I have time, I'm going to talk about some of the limitations of this assumption and how to extend this. But for now, let's say the relationship is linear and it is deterministic. Gamma 0 is its intercept. What it means is that the average degree by which each consumer prefers version 0 over version -1. And gamma 1 is the slope, which means basically if it is positive, it tells us that those who have a higher baseline willingness to pay also happen to care more about the differentiation. If it is negative, it is the other way. So this is basically sort of the skeleton of the model. And from this point on, what I would like to do is I would like to introduce a couple of results on what the optimal pricing policy looks like from the perspective of a monopolist that faces a demand curve based on the utility model that I gave you, and faces zero marginal costs. Zero marginal cost could be very easily extended, and we extend the results in the appendix of the paper. And I'm also happy, if I have time, to talk about what the extensions look like in terms of the results. But for now, for most of what I say, we're going to be focused on zero marginal cost. So we're going to characterize the optimal pricing policy for these two versions, P minus 1 star and P 0 star, based on the model parameters. And I'm going to do this in two steps. First, I'm going to look at a case where the differentiation is only vertical, namely when every single consumer I, at least weekly, prefers version 0 over version minus 1. And then after that, I'm going to move to a case where the differentiation is both vertical and horizontal, namely most consumers perhaps, or the majority of the consumers prefer version 0 over version minus 1. That doesn't have to apply to everybody. So that's the way we're going to do it. And I'm going to start with the first case where the differentiation is vertical only. Again, for your sort of, as a reminder, I'm going to keep this utility function on the top. And I'm going to give you a proposition. In this proposition only, I'm going to make some assumptions. First, I'm going to assume that this term mu I is distributed uniformly between minus sigma mu and plus sigma mu. And then, as a technical assumption, I'm just going to bound the absolute value of gamma I in order to make sure, so absolute value, sorry, gamma 1, the slope term, in order to make sure this term is always positive to ensure that differentiation remains vertical between the two products. Okay, so in this case, when you look at what the optimal policy is by the firm, it turns out that the firm, the monopolist, optimally decides to price discriminate, namely offer two versions of the product, if these conditions hold about the primitives of the model. I'm going to sort of breeze over them on this slide, but in the next slide, I'm going to sort of go back to talking about the intuition behind these conditions. When you do offer two versions, these are the prices. This is the price for your baseline version, and then this amount you could think of as your sort of upgrade chart. This P0, this P star 0 minus P star minus 1. And then if these conditions over here do not hold, then the firm optimally does not price discriminate, meaning the firm only basically sells version 0. You could think of that as a product choice. You could also model it as a pricing problem, because in a world in which there is vertical, the differentiation is fully vertical, as long as you price product minus 1 weekly higher than product 0, nobody's going to buy this product. So it is as if you're only offering basically version 0. Okay, so this is the result. What I would like to do now is I would like to talk about the intuition behind the conditions of the result, because that's what's going to matter to us when we talk about the empirical analysis and basically the application. The proof of the result that I gave, the theorem that I gave, for the most part, not entirely, but for the most part, becomes a special case of a result in a theory paper that I wrote. So for the proof of that, I will just refer you to that paper. On this slide, I'm going to focus on the intuition, in particular on the role of two parameters, sigma mu and gamma 1. Sigma mu, as I told you, is basically the standard deviation of the term mu I. When you think about the mu I, in a sense, mu I is modeling the heterogeneity among consumers in terms of overall valuations for the product, in terms of their price sensitivity. The higher the standard deviation of the mu I, the higher the heterogeneity there is in the market in terms of willingness to pay, say, for phones, if this is a smartphone product. If that is the case, it should not be surprising that a higher standard deviation mu I for the higher standard deviation sigma mu for the mu I parameter, it shouldn't be surprising that that makes it more likely that the monopolist would like to offer different prices, because the more heterogeneous the market, the more you're going to profit from price discrimination. However, this would be the case if there's availability of first or third degree price discrimination, if you could directly charge different prices to different people. But in the application that we're looking at, the only way the monopolist could basically try to get to different people with different willingnesses to pay, different mu I, the only way the monopolist could charge to them different prices would be through versioning based on K, right? So then the next question, to which hopefully our theoretical result would be speaking, would be whether this particular differentiation, let's say memory, is a good instrument for implementing this discrimination. Is second degree price discrimination in this case good? And the answer to that is not always a yes, even if there is heterogeneity among consumers. And that would have to do with, among other things, the sign of the parameter gamma 1. As I mentioned before, the gamma 1 parameter is a slope parameter. If it is positive, it tells us that those with higher willingnesses to pay for phones, those with higher mu I, which impacts your willingness to pay for both versions of the phone, those folks also happen to care more about the differentiation, about additional memory. Therefore, you could charge more for memory in order to charge more to them. But if it is the other way around, if gamma 1 is negative, then those with higher willingness to pay actually care less about memory. So you're not going to benefit as a monopolist by charging more for memory in order to get to your high willingness to pay. Okay? So these two parameters, again, I could talk about the intuitions behind other parameters as well, but in the interest of time, I won't. These are the ones, the two that I think are the most important, sigma mu and gamma 1. And this proposition speaks to it already. Now, I would like to sort of move on to a case where we allow for both vertical and horizontal differentiation. Yes, Jenny.
So I see in your setup you always have some vertical differentiation in there. Is that because you want gamma 1 to be positive? If it's purely horizontal, then they can be like they're not really correlated with the baseline utility. Is that a good way to think about it?
I would think so. So actually, some of these we are still trying to sort of figure out. With this proposition, you would for sure need it with the previous, with the one that I just gave, proposition 1. With the second proposition, as I'll very shortly show you, really does not depend on much. At this point, anything could go. You don't even have to care about gamma 0 being. So hopefully once I will give this, it will clarify a little bit. So now we're going to add horizontal differentiation, in particular in the form of adding epsilons. So first of all, we're not going to have sort of restrictions that we had on what this term looks like. We're not going to have those anymore. By the way, I'm also no longer assuming that mu I is distributed uniformly. And I'm also adding these epsilon ik's, which tells us, and I assume that they're distributed extreme type 1, which tells us that now, under most conditions, there's always some consumers who prefer each version over the other. As you may know, if you have done some theory work on second-degree price discrimination, the moment you add these error terms, all of the mechanism design tools that we have in place, basically looking at direct mechanisms using basically the revelation principle, all of those go out the door. So no longer can we use those methods to arrive at a characterization for optimal pricing. Here, however, we showed that at least a partial characterization, which is very simple, could be obtained even though we have these additional terms which make the sort of optimal pricing analysis a little more difficult. Let me give you the characterization. Our second proposition says the optimal mechanism, pricing sort of P star minus 1 and P star 0, satisfies the following condition, which says P star 0 is larger than P star minus 1 if and only if gamma 1 is positive. So basically, in the previous result, I showed you a condition that said a lot of parameters matter. Now, all of a sudden, it is only one that matters. To be clear, the result simplified not because we have simplified the model. The model that I'm showing you here is actually more general than the previous model. Because it has the error terms, it does not sort of bound the absolute value of any parameter here. It does not make a functional form assumption on the distribution of mu I. Nevertheless, the result is simpler. And also a corollary which would be useful to notice is that this result does not depend on any assumption, this normalization of the extreme type 1 error term, which is normalized to 1. If you make the variance of the epsilon terms arbitrarily small, as long as it is positive, this simple result over here holds. So let me, yes, Nakia.
So does it depend on this particular functional structure of horizontal differentiation in the sense that, as Jianlin said earlier, like we could introduce an alternative horizontal differentiation through gamma 0, gamma 1 mu aspects as opposed to product-specific unobservable terms, right? So is it going to depend on this particular assumption, or it's generic to that extent?
Okay, let me try to make sure I understand your question, because here I'm no longer imposing assumptions on gamma 0, gamma 1, and even the distribution of mean. So basically, there's no, I mean, there's this assumption that the dependency is linear, but outside of that, there is no assumption. So to the extent that there,
yeah, the
yes.
assumption seems to be that there's this epsilon term. It's going to add an extra dimension of horizontal differentiation, like symmetric unobserved product differentiation, Ackerberg's, I forgot the other guy, sense, right? So no matter what the observable part of the utility is, there is always some subsegment of people who prefer inferior product because of the high draw of epsilon. Seems to be that's triggering this part of this result that the inferior product can be priced higher potentially. And if alternative mechanism is the main driver, maybe that part is gone because we are not adding a dimension of product attribute.
I see. I would guess that this does impact the results. I think, you know, for me to be 100% sure, I would have to solve the other problem as well. It might prove a little more difficult. But if I were to give you my best guess, I would say that this does impact the result. But I will also tell you later, if I have time, some things about approximations and, you know, whether you could see empirically how much of the impact is coming from this versus other.
Makes sense. Thanks.
Anytime. But before that, let me focus on the intuition itself. Basically, it still needs to be investigated why this counterintuitive result emerges, why only gamma 1 matters, and in particular, why charge more for the worst version, even under very large gamma 0, okay? Because a large gamma 0 means, on average, consumers have a higher willingness to pay for version 0 by a wide margin. The intuition that I'm going to give you here is incomplete. We'll probably not have time to even talk about why it is incomplete, but it is incomplete. But I hope it is useful. In order to get a very complete intuition, I guess the only thing to do would be to engage with the proof. But again, I hope this intuition at least does some help in sort of making sense of this result. Part of the answer about why this result emerges is about how many versus whom. The large gamma 0 will tell us that more customers will prefer version 0, basically say high memory phone, over sort of version -1. But a negative gamma 1 tells you something about the highest willingness to pay customers. The negative gamma 1 says the highest willingness to pay customers prefer the worst version, okay? Prefer the version that the majority of the market think of as the worst version. I'm going to give a simple example of this very soon. And if that's the case, at least I hope this somewhat clarifies why gamma 1 might have an important role here and might even lead to the otherwise worst product, or sort of on average worst product, to be priced higher. So that's the first question. I hope this intuition helps. The second question is, does this new result render the previous result that we had irrelevant? And the answer to that, and this, Takeaki, might also sort of relate to the points you made, the answer to that is no. The previous proposition does approximately hold if there is little horizontal differentiation emerging through the error terms. And what do I mean by approximately? Now that we're sort of about to shift gears to talk about empirics, let me summarize my main lesson in the following sense. The degree of horizontal differentiation matters. If there's non-trivial horizontal differentiation, perhaps it will be fine to, perhaps it would not be a crazy idea to price the on average worst version higher if your gamma 1 is negative. But what do we mean when we say there's non-trivial horizontal differentiation? How could you measure it in an actual market? Here's one way to measure it. Set the prices equal and see if the demand ratio is something non-trivial. If that is the case, if under equal prices, version -1 garners a non-trivial share, that means there is at least some degree of horizontal differentiation. However, if horizontal differentiation is almost non-existent, namely if you set the prices equal and all of the demand goes to only one product, then perhaps you're fine sticking to the recommendations from the previous proposition, which says you never have to worry about, you never have to consider charging more for the product that is on average worse. One would guess perhaps that the smartphone example with memory levels would fall under this category. If prices of different memory levels are equal, my guess would be that very few people, if any, would buy lower memory. To think about another example, let's say OpenAI is thinking of pricing its different products. And let's say we are thinking about a better model versus a sort of a weaker reasoning model, which happens to be fast. Just as a made-up example, imagine a small but price-insensitive portion of the customers prefer speed. For some reason, imagine hedge funds are into using LLMs for making some financial decisions, investment decisions. And they require speed for sort of processing information that newly arrives. If that is the case, and if they're not a trivial part of the market, then perhaps you might profit from at least considering optimally pricing the faster, on average, worse version higher than the sort of better quality reasoning version. Okay? So this is just one example. I want to sort of illustrate why you would need to think about models in which both vertical and horizontal differentiation exist. Now I want to sort of switch gears and go from results that talk about basically optimal prices to results that could help us design experiments and do empirical. The results that I gave so far, which I call optimal mechanism results, basically take parameter values and tell you something about what the optimal pricing policy is, which were propositions 1 and 2. Now I want to sort of think about results that take in data patterns and tell you something about what the parameter values look like. If you put these two types of results together, effectively you will have a machinery that takes in data patterns and tells you something about what the optimal pricing mechanism is. And that is exactly what we as empirical scientists are interested in. So that's where I'm going to start. In particular, I'm going to try to give you results that help identify those two parameters, sigma mu and gamma 1, which I told you are important for optimal pricing. The other parameters are also identified. If I have time, I'm going to talk about their identification. If not, happy to talk offline. So let's start with sigma mu, and let's try to sort of devise a test that will help speak to it. I'm going to first define a quantity, which, I don't think, I'm the first person who's thinking about it. This has been around, but I'm going to try to sort of make a connection between that and sigma mu. Let's think about cross substitution rates in the following sense. Let's say we start with a vector P, right, vector capital P of prices P minus 1 and P0. Let's say we pick a version K, whichever of them, and change the price of that version by a margin of R, but keep the price of the other version K prime fixed. So in that way, we get to new prices. Basically, we call this new price vector P tilde. And then we define a quantity, which I call the cross substitution rate. It's this mathematical object. What it says is basically what portion of those customers who abandon product K substitute to K prime. If I increase the price of my high memory phones by $100, some people abandon that product. What portion of them substitute to the lower memory phone as opposed to buying something else, basically leaving my sort of product assortment? Okay, let's call that the cross substitution rate. Our proposition, which we call partial market test, speaks to how observing the cross substitution rates could help you say something about sigma mu. The idea is, if you implement a test like this, which we call a partial market test, and change only the price of one of the versions, and look at the cross substitution rate, you could say something about sigma mu. If the cross substitution rate is the rate that would be basically implied by a loaded model, then sigma mu is 0. If the cross substitution rate is higher than that, then sigma mu is positive. The basic intuition is that if we have a very high cross substitution rate, we should expect a large standard deviation, by standard deviation from mu I. And the intuition behind it is same as basically loaded versus nested loaded, right? If the cross substitution rate is very high, it means that there is some parameter that nests these two products. There's some parameter that impacts the willingness to pay for both of these versions, and that governs most of the choices that we see. Basically, that has a high variance. That parameter is mu I, okay? So basically, we get something about the heterogeneity of the willingness to pay overall for all products in the market by looking at the cross substitution rates. So that is the first test. Yes, Takyaki.
So I'm not sure if it's the right time to ask this particular question. Please feel free to defer, but I'm still trying to figure out what's unique in this particular environment that doesn't map into the typical BLP environment in some sense. In the BLP environment, there are product attributes, and there are random coefficients in there that's going to create a correlation of preferences across products. And identification is exactly what you described in here. So far, it seems like this is kind of like a special case of a BLP environment. Is there something that this model has that the typical BLP does not? Or is it some other kind of additional parts that I am missing?
I see. I guess it depends on what you say. Actually, I think this is a good place to ask this question. Perhaps we could have waited one more slide, but I was done with this slide, so I can go to the next slide. And this will be the best place to ask this question. So it depends on what you think of as typical BLP. So most of the BLP models that we see do not allow for covariances between random effects. Right? Typically, we only allow for the diagonal terms. Even when we do allow for off-diagonal terms, the identification of it, to the best of our knowledge, is not well studied. So when you think about this term, basically this gamma 1 term is proportional to the covariance between random effects. You're correct to observe that this looks a lot like BLP. I mean, I haven't added the C terms yet, but you're basically right. This is BLP. You could think of mu I as a random effect on the constant, right? You could think of gamma I as the random effect on, or the part of gamma I that excludes gamma 0 as a random effect on this piece. And gamma 1,
effect,
exactly. So it's basically a product fixed effect model where there's covariance between the random effect on the constant and the random effect on a product done. So that and our theoretical propositions tell you that this covariance between random effects is absolutely essential in optimal pricing, right? But when you look at the identification of covariances in BLP models, to the best of our knowledge, and I've also talked to Steve Berry about this, the identification arguments for these off diagonals, the literature on that, in our view, is very much thin. The key thing, the best that we found was in a working paper by Gandhi and Hude. I think it is, I think it's the Stiller working paper. They do some Monte Carlo simulations that identifies the off-diagonal terms, and they do not provide an intuitive argument. But what you could see there is that what they use is a much larger number of products relative to features, so that the features in the core, basically the different values of the features relative to each other, would change across those products, so you could say something about the covariance of the random. That is not the case in second-degree price discrimination models. And many of them, you only have two versions. Even if you don't have two, you only have very few, okay? So basically what we're putting together here is a combination of 3 points. One, the off-diagonal terms matter. So, sorry, one, there's off-diagonal terms. Two, by the theoretical analysis of screening models from the mechanism design literature, this off-diagonal matters a lot, perhaps more than anything else in optimal pricing. Three, in applications where this matters, you don't really have many products, and we don't know how to identify that yet. So we need a different approach. And our next test provides you with that different approach. The previous test that I gave you is useful, but I wouldn't call it innovative, because it effectively boils down to loaded versus nested loaded, but it was necessary, hence I presented it. Now, I would like to present to you the next test, which helps identify basically this term which is proportional to the covariance between these random effects. And now I define another sort of observable quantity in the data. I call it, yes, Yanlin.
So I see that you have this gamma 0, gamma 1 thing to correlate with the baseline mu I. Can I not have mu I but have bi, so the price coefficient is different, and then you have the thing to correlate with this bi? Would that also go through?
I think so. So once I present to you this test, maybe you could judge for yourself. My guess is that it would. But but I think it's maybe this is a good time to ask, why not use BI? Why use mu I instead of BI? My biggest issue with using BI is that, and that's a separate matter, it's not necessarily related to the core topic of this analysis, but I think it's important, perhaps would warrant a discussion. I think when you use BI, everything about the functional form assumptions about BI becomes absolutely important in the decision making. For a second, imagine we assume BI is normally distributed, which, by the way, many published papers that use BLP, even in the sort of top business and econ journals, assume that. But for a second, when we think about a normally distributed BI, it means always there's a non-zero measure set of customers that actually prefer higher prices, right? That means the optimal price is always infinity for any version if you're using the model for optimal pricing. Yes, Sumit.
Just following up on this question, so my understanding is that this would matter here in a sense that if you have you need special regressors in this BAP models to identify these, so you need here price is a special regressor. So let's say we have we see fully change in two prices and we look at these diversion ratios. So I think it would be hard to identify here full matrix with the diagonal variances and the covariance. So you can either remove the diagonal and get the covariance, or remove the covariance and get the diagonals. If you just see two prices, right? Because it's only two instruments and you're trying to get three parameters. So here you sort of, how I see it, you remove one diagonal and bring back covariance. Because you kind of link them, right? So the mu I shows up in both. So you sort of the variances are linked by gamma 1, right?
I see.
Is that a good way to think about it? Because we have only two special regressors, and that's why we can only have 2 degrees of freedom.
Maybe. Yeah, maybe. I will have to think more about it. My best answer now is that that's probably right. But even then I think maybe actually that would be a good way to think about the role of theory. Theory says, look, you need to have the diagonal. So whatever it takes, you need to do it, because the diagonal matters a lot in figuring out the optimal pricing, because that is what tells you what is a good instrument for discrimination. There is that, but I hope the test that I'm going to give you, because it's not just about degrees of freedom. Degrees of freedom says if you have very many data points, things are identified. But I think having tests that are intuitive could go a long way beyond degrees of freedom type identification arguments. So maybe once I give you this, you would be able to judge whether we're doing something beyond that. Yes. So in this second test, let's say we have vector P of prices P minus 1 and P0. This time, instead of changing only one price, I change both of the prices by the same margin. Note that what this does is that it shuts off cross-substitution between the products, because the comparison between the two products from the perspective of any customer remains the same, right? And now I define this quantity, which I call the relative response rates. It just tells you how does the ratio between the demands for the two products changes. You change both of the prices by the same margin. How does the demand ratio respond to a price treatment that shuts off cross-substitution? And I would like to argue that this is the right sort of metric to directly identify the slope parameter or the covariance parameter gamma 1. Here's the next proposition, which we call the total market test. This proposition says that the relative response rate between versions minus 1 and 0 is larger than 1, basically if and only if gamma 1 is positive. Let me tell you the intuition. Again, the proof is somewhere in the appendix, but I don't think that will be as useful as an intuition. The intuition is actually kind of simple. Again, let me sort of go back to sort of the phones example. Let's say you increase the prices of both of your phone versions, high and low memory, by the same margin, basically making the comparison between them the same for all individuals, but you observe that the demand ratio between them changes. Now a smaller portion of the market buys the low memory phone. What does that mean? It means that customers will have a lower preference for additional memory, namely those with low gamma I. Those are more likely to drop out as you increase the prices uniformly. Because as I said, when you're increasing the two prices by the same margin, you don't induce any cross substitution. So any change that you see in the demand ratios between the products could only come from the different rates of basically the comparison between marginal and inframarginal customers in terms of what sort of preference they have over the differentiation. So if you increase both of the products, both of the prices by the same margin, you see more of the customers of the low memory dropout. It means that those who happen to have a lower preference for additional memory, namely those with lower gamma I, happen to also have a lower mu. And that is why they drop out faster, which means your gamma 1 parameter is positive. Again, I think if you did this, if you did this with BI, you could get a similar result. But basically, once we do it with mu I, this is what it sort of helps identify. So it helps directly speak to the covariance parameter. Yes, Takyaki.
Just wanted to make sure I understood this thing correctly. Your discussion reminds me of this Ackerberg-Reisman's 2005 paper. Now I remember the second author. But your results specifically is tailored for the identification of the off-diagonal part of the matrix. Am I right to understand it that way?
I have to think. I don't have my best answer now, but I will sort of need to sort of go over that more carefully. I would say the closest argument to this that I have seen are from two separate literatures. One is the Steve Berry and Phil Hale paper on identification with aggregate data. The working paper version of that had an example which got cut from the published version. This is basically a diff and diff argument, right? You could think of this ratio as a diff, and I say, as I change the price, how does that diff change? This sort of diff and diff argument, the closest thing to it that I've seen is an example in an unpublished version of the Berry-Hale paper.
So Ackerberg-Reisman 2005, they have got this discussion that you change one of the prices individually versus you change all of the prices simultaneously, and that these two different substitution patterns will give us different identification constraints. They talk about the nested logit environment, and so they don't have the off-diagonal, but it seems like you're exploiting the exact same variation, but specifically for this off-diagonal thing. So.
Yeah, I remember that, but for some reason it didn't click for me back then. I have to revisit it. Yes, again, we have to work with the off-diagonal because the theory says if you want to, maybe for some other models, it would not be of first order importance, but for this, the off-diagonal is the thing you want to catch. And this is a direct test for it.
Thanks.
So thank you. I have 12 minutes, right? Yes, you can.
Hi, Soheil. Sorry, just a very quick question. So, how do you think about micro moments as an alternative?
Well, we are thinking about it as we speak. We're trying to sort of look at that. It might help us. It might help us actually even go beyond the sort of linear and simple relationship between mu I and gamma I. But even with that, we still think these results matter a lot because often by micro moments, you probably mean things about characteristics of consumers, right? Especially characteristics that could derive the covariation. My guess is that the best characteristic that could help sort of speak to that is income. Most sellers don't have that. As a result, we think this is useful even if you have access to those characteristics. But I agree, even sort of, you would still need to think about and say something about micro moments. In this version, we're not talking about it, but as we speak, we are working on it. Hopefully we will have more on this to say hopefully in the next month or so.
Yeah, thanks.
Oh, anytime. So let me very briefly tell you about the experiment design. Effectively, the experiment design is going to have these two types of tests in it. Partial market tests, which change the price of only one product, and total market tests, which change the price of both by the same margin. Here, I'm sort of thematically showing this to you on a space where one of the products is basically price of version -1 is on the horizontal axis and version 0 on the vertical. And here I'm assuming that under the control group, the two prices are the same. It doesn't really have to be. The only things that are essential about this design is that you have those two tests. Partial market tests based on proposition 3 help identify sigma mu. Total market tests based on proposition 4 help identify gamma 1. The other parameters A, B, and gamma 0 are also identified. In the interest of time, I'm going to skip how. I'm going to skip this slide as well. Empirical model and estimation procedure. The empirical model is basically the same as what I gave you so far, except that you need to have the additional pieces in order to basically take it to data. Three differences. One, now we have an index M added to everything because we need not only the individual and the product, we also need the market. You don't have to have constants, you don't have to have scalars for A and gamma 0. You could have it basically as a function of market characteristics. Later, we could also incorporate micro moments. And finally, another change that we have is these C and K terms, which are basically the terms that allow you the structural errors that allow you to estimate this as a BLP. So this is effectively BLP now, which means now we have a model of price discrimination that is sort of motivated by theory. The theory tells us what are the parameters that are key to estimate. We have the tests for them as well. And now this last slide tells us we have the procedures, we have the estimation procedures for them as well. We are able to use basically the nested fixed point algorithm by Berry, the contraction mapping style, Berry 94 algorithms to estimate it. We could add individual level moments as well, as you mentioned. We're not doing that yet. And today, for the rest of today, I'm going to be sort of working with constant A's and constant gamma 0s. But again, in terms of the algorithm, it works just like that if you add however many characteristics you need. Okay, so in the very few minutes that I have, let me tell you a little bit about the application. I'm going to try to be brief. I would like to sort of use this to sort of showcase that flexibility of the framework. The application is international airline in India, and we look at the time of purchase and seat selection. I'm not allowed to say the name of the airline, by the way, even though I gave you the name of the affiliations of all of my co-authors. So we're going to look at a two-dimensional experiment on discount depth and whether there's a deadline. So everybody who purchases a flight ticket, before they make a decision about seats, not everybody, but a randomly selected subset of them, are going to be shown an ad like this. It says 30% off every seat if you book 3 days prior to departure. They're also shown, some of them, another sort of group is shown the same ad without the deadline. So if you think about the differentiation as a timing of purchase, then basically showing this ad means only lowering the price for the early purchase product, and showing this ad without a deadline means lowering both of the prices. So we do it by 30% and we do it by 60%. So we basically have our partial and total market tests. Very briefly about the data and setting: international carrier in India, 3-week-long experiment on seat selection for those who purchase tickets, 160 routes, 10,000 flights, 160,000 total customers. We have two groups of customers: those who purchase flight tickets more than 14 days prior to departure. To those, if we give a deadline, we give a 14-day deadline. And those who purchase the flight ticket 3 to 14 days prior to departure. To those, if we give a deadline, we give a 3-day deadline. This is the data set I'm going to show you results for today. A little more on why this is a good setting, why seat selection is a good setting. One reason is that it affords us flexibility in experiment design. We really wanted to make sure we would see sort of some effects. We wanted to make sure we could implement large sort of deep discounts to make sure we see sort of treatment effects. 60% discount would not have been possible to implement on actual airfare. So that's one reason. But in spite of that, ancillaries are not a small market on their own anyway. They are a multi-billion-dollar market in the US, for example. Another good thing about this environment is that it's effectively a monopoly market. Nobody's going to sort of cancel their airfare because the seat is expensive. And this sort of makes it more sort of suitable for our methodological framework. This is not to say that examining this price discrimination question under competition doesn't matter. It is just that we think that will be the next step. And the first step that we're taking here, we think is useful to sort of look at a monopoly market. And finally, this is a market where vertical and horizontal differentiation both are expected. You would expect most people to want to purchase late, but some to purchase early. So, and given that we showed in the theory analysis that that part of that sort of thing also matters, I think it is useful to have that in the applications. Okay, let me show you some summary stats very briefly. Basic things that you could see is that when you look at these treatment groups, when you give a discount, overall demand increases. When you give a discount without a deadline, the demand increases even. But I would like to focus on three summary stats, which I think are useful and showcase the sort of versatility of our framework. First, let me show you the demand ratio between the products under equal prices. As you see, the share of early purchase relative to late purchase is not close to zero, meaning there's some horizontal differentiation when the share is not close to zero under equal prices, but it's also not very close to one, which means there is some vertical differentiation as well. So both exist. The second piece that I would like to show you is the cross substitution rate, which is well above the logit rate, which tells us that there is some heterogeneity in the market that ideally the seller would like to price discriminate based on. The next question is whether time of purchase is a useful instrument to implement this sort of price discrimination. And that would be sort of shed light on with our relative response rates. It is very close to one. What does it mean? It means that when we give a similar, basically uniform discount without deadline, basically for both versions of the product, early or late, the ratio of the demand between early and late purchase does not change. What this tells us is that when we lower these prices and allow in more price-sensitive customers, we don't see a shift in preference between early and late, which tells us that more and less price-sensitive customers do not, on average, differ much from one another in terms of timing of purchase, which implies that using timing of purchase to discriminate between high and low willingness to pay customers is probably not going to work. Before I show you results, I would like to emphasize that this is a sign of the versatility of this framework. We are able to speculate things about what the optimal prices are like, even before we have estimated a structural model. And I think that's a useful thing. So now let me show you the estimation results. As you see, gamma 0 is positive, but not too large. Sigma mu is positive and significant, and gamma 1 is small, as we expected. When I show you, so this is model fit results are good. Let me show you optimal pricing results. They told me that I need to normalize the prices to 100 because otherwise the firm would be identified. So these are the normalized prices for you. These are the prices that you see in the data normalized to 100. Our simulation results suggest that the optimal prices are above the prices the firm charged, and we actually recommend they increase the price, and they did it. But as you see, our results suggest that optimally, you don't want to charge P1 and P0 that are too different from one another. We also compare the optimal prices when the pricing is flexible to a regime where you could optimize the price, but you have to give the same prices early and late. And you see that the profits do not really change that much. By the way, the revenue, consumer welfare, social welfare numbers are only useful to think about in comparative terms. In absolute terms, you can't because prices are normalized and the absolute value of these are not meaningful. But as you see, all of these results are in line with what we guessed just by looking at these numbers and applying our propositions, which again, I think is useful. I had additional simulations in place to show you what the results will be under other values of these simple summary statistics. I won't have time to go over them, but what I would like to emphasize is that our framework allows you to say something about allows you to guess what will be estimated in the structural model, and allows you to guess something about the optimal prices even before estimating the model, which again, I believe in many applications could prove useful if there's not enough time or not enough resources to go ahead and estimate a full-fledged structure. Further research, and do I have time? No, I don't have time. So let me just thank you for being here.
All right, thanks, Soheil. So we can end the formal part of the presentation now.